Now let's look at our second sort of scenario, and that is changing the volume and or pressure here, remember they work together, of a gas phase reaction. So if I think about changing the volume of my container, right, for a gas phase reaction. So if I decrease the volume of the container, it's going to increase the concentration of the gases. Why does that? Well, because we have the same amount of material in a smaller volume, and that's going to increase the concentration, right? So if we have the same amount in a smaller space, well, it's a higher concentration. In terms of pressure, right, we're increasing the pressure here. So this is following Boyle's law, right? Decreasing the volume causes the inverse effect on the pressure. So decreasing the volume will cause an increase in the pressures of our gases. It does not change concentrations of solutions, right? So this only affects gas phase reactions, right? So if I have a solution and I put it in a smaller container, right, it doesn't change the concentration, right? This only applies to gas phase reactions is sort of the idea here. Now, as the pressures increase, right, so we got more pressure. So how can Le Chatelier respond to a change in pressure? Well, if possible, the reaction can shift one way or another to try to lower the pressure. Or in other words, we're going to try to lower the moles of gas, right? Because if I can lower the moles of gas, according to PV equals nRT, right? If I lower N, right, that should have a direct effect on P, right? Less gas, less moles of gas, less pressure. So if I increase the pressure by decreasing the volume, the reaction can respond to try to shift toward the side of the reaction with fewer moles of gas. That'll serve to lower the pressure. So when the volume decreases, causing the pressure to increase, we shift toward the side with fewer gas molecules to try to lower the pressure. So that's sort of a brief summary of what's going to happen. So let's look at this in a little bit of a picture. So let's say we have our picture here. So this is the scenario that we were just looking at. So I lowered the volume, which caused the pressure to go up. So we got an increase in pressure here. So let's look at our reaction. So we have N2 plus 3H2 goes to 2NH3. So on the reactant side, we have 4 moles of gas. On the product side, we have 2. So if I want to lower the pressure, I'm going to shift toward the side with the fewer moles of gas. So in this case, we're going to shift toward the products to lower that pressure. So for this particular reaction, so we have to understand that for this scenario, for this disturbance, it's going to depend on the particular reaction, right? So depends on which side has fewer moles, right? Whether it moves toward the reactant or the product. In this case, since we have fewer moles of product, we're going to move toward the product side. Now, of course, decreasing the pressure is going to have the opposite effect. So if I remember decrease pressure, or excuse me, let's do that. Let's start at the beginning here. So if I increase volume, like I'm doing here, that's going to decrease the pressure. So what is the reaction going to do? It's going to try to increase the pressure, and it's going to increase the pressure by shifting toward the side with the more moles of gas. So in this case, we're shifting back toward the reactants. So basically, we're going to try to counteract the pressure change by shifting toward either the side with more or less moles of gas to try to increase or decrease the pressure to balance out whatever change that I make. Now, if the reaction has equal moles of gas on both sides, well then a change in the volume won't have any effect on the position of equilibrium, right? The reaction can't respond in a way to balance that out, so it will just not respond, right? It won't affect the equilibrium position. Now, one other comment about ideas in gas is if I have a gas that is not part of the balanced equation, so in other words, I add some gas that isn't a part of it, so this would be down here called adding an inert gas, it's not going to have any effect on the position of equilibrium because it does not affect the partial pressures of the reacting gases. So I can add, I was going to change the total pressure, but we're not changing the individual pressures, and so there's no effect on the equilibrium. So just to summarize here, adding a gaseous reactant will increase its partial pressure, causing the equilibrium to shift to the left or the right, just like we talked about with concentration of solution. So we get the same effect on pressures. You know, if we add gaseous reactants or products, we're going to have the same shifts that we talked about earlier. But if I add an inert gas, it has no effect because I'm not changing the pressures of my reacting gases or my product gases. All right, so that sums up the effect of volume and pressure ideas on equilibrium. Now, the last thing we're going to look at is the effect of temperature. All right, so the third condition that we wanted to discuss was how temperature changes affect the position of equilibrium. Now, in order to do this, the first thing we have to know is what kind of reaction it is. So the effect of temperature depends on whether a reaction is exothermic, meaning it releases energy, or if it's endothermic, meaning it absorbs energy, right? So these two types of reactions will respond differently to temperature changes. So the first thing is we have to know which type of reaction is. And one thing that can make, once we know this, one thing that can make it easier to study the effects is to treat heat as a part of the reaction in terms of, is it a product or is it a reactant? So in an exothermic reaction, heat would be a product. In an endothermic reaction, heat would be a reactant. And so by doing that, then we can sort of go back to what we talked about with concentration and, you know, look at, is heat going up or is heat going down as we change the temperature? So even though heat is not typically written as a reactant or product, and not should it be, it can help, by doing so, can help us understand this particular concept. So let's first look at an exothermic reaction. So an exothermic reaction is going to have heat as a product. Now, if we think about what changing temperature means, right? So remember, temperature is the measure of the average thermal kinetic energy. So if I increase the temperature, that's like adding more heat, right? So that's like adding heat. If I decrease the temperature, that's like removing heat or removing a product. And so by analogy to what we looked at with the concentration change, we can come up with the following ideas. For an exothermic reaction, again, heat is going to be written as a product. So if I raise the temperature or add heat, that's like adding a product, and the reaction is going to shift toward the reactants. And so For an exothermic reaction, raising the temperature is going to push the reactions toward the reactant side. Now, one of the things that I got to mention right away is that temperature changes will change the value of K, right? Because notice we didn't disturb by changing the amount of material. So when this reaction shifts to the left here, I'm going to increase the amount of N2 and H2 and decrease the amount of NH3. So if, again, K is products over reactants, so this is my K initial here. If I see this shift to the left, what's happening here? Well, my reactants are going up, my products are going down. This is going to lower my K. So we're going to lower K here. And so my K2, or my K initial, right, will have my lower amount of P and my higher amount of reactants. And so K2 will be lower than K1. And so the ultimate effect here on an exothermic reaction, raising the temperature, shifts to the left, resulting in a smaller K, which should make sense, right? Because remember, a smaller K indicates a reactant-favored process, right? A process that doesn't go as far toward the products. Now, of course, exactly the opposite is going to happen if I remove heat or lower the temperature, because that's like removing a product from an exothermic reaction, so it's going to push the reaction toward the products, which is going to cause K to get bigger, right? It's going to raise up P, lower R, which is going to increase our P to R ratio, making K bigger. And so, lower temperatures, lowering the temperature of an exothermic reaction is going to result in a more product-favored reaction, of course, with the larger K. So what that means, right, is sort of from a chemical point of view, right, is that if we have an exothermic reaction, if we want to maximize the product formation, we probably want to think about running that reaction at a relatively lower temperature. Now, we can't put a number on that because a low temperature means a whole lot different things from one reaction to another, right? For one reaction, a low temperature might be 100 degrees. For another reaction, a low temperature might be 300 degrees, right? It's all relative for each given reaction. But if we are running a reaction at a temperature and it's exothermic, one thing we could try to move more product or create more product is to run that at a lower temperature, because that will favor product formation. Okay, so that's an exothermic reaction. What about an endothermic reaction? So everything is just simply reversed. For an endothermic reaction, heat is a reactant. And so if we think about the Chateliers principle, we're going to shift away from added heat. If we add a reactant, right, we're going to shift toward the products. So if I raise the temperature of an endothermic reaction, we're going to shift it toward the products and toward a larger K. So you can see it's exactly the opposite as an endothermic reaction, or as an exothermic reaction. So increasing the temperature in an exothermic, that was like adding a product. Increasing the temperature of an endothermic reaction, that's like adding a reactant. And so they have the opposite effects. So for endothermic, adding heat, it's like adding a reactant, which shifts away from that reactant to make product. If I lower the temperature or remove heat, it is like removing a reactant, and it's going to drive the reaction toward that removed reactant or toward the left, which is going to result in a smaller K or a more reactant favored. So with an endothermic reaction, we probably want to try to run it at a higher temperature, right? So while exothermic reactions might be favored at lower temperatures, endothermic reactions are probably going to favor product formation at a bit of a higher temperature, right? Since adding heat will shift it to the right. Okay, so if we summarize endothermic, right, it's just the opposite of what we saw for exothermic. Increasing the temperature of an exothermic reaction will, that should be endothermic. Increasing the temperature of an endothermic reaction will favor products, increase the value of K. Decreasing the temperature of, again, an endothermic reaction will decrease the value of K because it'll push toward the reactants. So this sort of sums up the effect of temperature. Now, we can illustrate this idea by oscillating a reaction, right? So let's just look at this reaction we've been looking at, the equilibrium between N2O4 and NO2. So this is a endothermic reaction. So we can see we've written heat as a reactant. So if I raise the temperature over here, right, so this is going to be a higher temperature, well, that's going to push the reaction to the right, and we see the brown gas indicative of the NO2 of the product. Now, if I lower the temperature, I can cause that equilibrium to shift, right? Lowering the temperature is going to shift toward heat, try to generate more heat, right, to counteract the lowering of the temperature. So we're going to shift toward the colorless N2O4 reactant, as we see here. So we can get this reaction to shift back and forth from the colorless N2O4 gas to the colored NO2 gas by oscillating the temperature, right? And we can so then illustrate, the effect of changing the temperature on an equilibrium system, in this case for an endothermic reaction. So, changing the temperature, again, another disturbance of the equilibrium. Now, the one big difference, of course, with this third example, this temperature, than we saw with changing concentrations or pressure volume changes, is that in this condition, under temperature changes, we don't reestablish the same value of K. We generate a new value of K. Right? Because that equilibrium constant is going to be temperature dependent. So we don't try to reestablish the same equilibrium. We reestablish a new equilibrium at that given temperature. All right, so that kind of wraps up what I want to talk about with Le Chatelier's principle, except for one last comment, and that is the effect of a catalyst. So back when we looked at kinetics, right, we saw that using a catalyst is a one way that we can speed up a reaction, right? In other words, we can make a reaction move faster. Now, when we think about an equilibrium system, what we have to understand is that a catalyst is providing an alternate mechanism. But a catalyst doesn't just affect one way or the other. So a catalyst will work on both the forward and the reverse conditions. So if a reaction is in equilibrium, right, it's going to move faster in both directions. Right? So ultimately, the catalyst has really no effect on the equilibrium, right? What it might do is it might speed up how fast we reach equilibrium, but it's not going to speed up, or it's not going to change the position of equilibrium. In other words, it's not going to affect the value of K or change the equilibrium concentrations of that reaction. Right? It's going to speed up how fast it gets us there, but they do not affect the position of equilibrium. All right, so that wraps up, summarizes our introduction to equilibrium chemistry. Now, in the following 2 chapters, we will be looking at very specific examples of some types of equilibrium reactions. So we're going to look first at a whole chapter on acid-base interactions, and then we're going to look at some other types of equilibrium in the following chapter. All right, so if you have questions about any of this, make sure to reach out. Make sure that you're watching the other videos that I've provided to try to elucidate some of these ideas, maybe give some more practice problems or examples of solving problems, or maybe give some more detail on specific aspects of the material.